In this video, we're going to prove 3 facts about matrix inverses. First one says that if A is non-singular matrix, that is A has an inverse, then that inverse is also non-singular. And the inverse of A inverse is A. The proof is very straightforward. Okay, if A is non-singular, that implies that A inverse exists. Implies A inverse exists. And we know that A times its inverse is the identity. Now, A inverse is, right now, think of A inverse as just a matrix. Maybe CB instead. Instead of A inverse, CB. But wherever we see B, we're going to write A inverse. Okay, that is, if A times B is I, that means this matrix must be the inverse of B. That implies the inverse of that matrix, which is A inverse. The inverse of that matrix must be A. So let's see. We assume that A is non-singular, and we showed that the inverse of A inverse is A. We showed that. That is, we showed this part. Okay, did we show that A inverse is non-singular? Of course we did. Why? Because we found the inverse of A inverse. By definition, which is A. That means by definition, A inverse is non-singular. Okay, that's the proof of A. Now, to prove B, we're told that A and B are both non-singular matrices. That means A and B have inverses. We want to show if A and B have inverses, and of course they are appropriate sizes, then AB is also non-singular. And the inverse of AB is B inverse A inverse. Again, if I can show that the inverse of AB is whatever, that means AB has an inverse, and hence AB is non-singular. AB is non-singular. Now, okay. So, I'm saying that the inverse of this is that. This one's so simple I can put the proof here. Well, if that's true, if the inverse of AB is this matrix, then AB times B inverse A inverse better be the identity. So we're going to invoke the associative law a lot. This is AB times B inverse times A inverse. I'm thinking of this as one matrix times two matrices. So I can move the brackets. Now I'm going to think of AB as two matrices times B inverse. And once again, I'm going to move the brackets. Now this is the identity. So we have A times the identity times A inverse. But A times the identity is just A. And when I multiply that by A inverse, yep, I get back A. Sorry. I get the identity matrix. That is, I was able to multiply AB by something and get the identity. Hence, the inverse of AB, the inverse of this, is whatever I multiply it by, which is B inverse A inverse, to get back the identity. So I proved that theorem. Now, just want to point out that when you have AB inverse, switch the order and take inverses. That's exactly what I have here. Okay? So you don't need that for the proof. And right here is the proof of B. Now for C, this was proof of A. The proof for C is if A has an inverse, that's what it means. If A is a non-singular matrix, then we have this. Okay, that is the inverse of AT is equal to A inverse T. If I can show that's the identity, then the inverse of this, which is AT inverse, which would be AT inverse, will equal to A inverse transpose. If I can show that that is the identity, I'll be okay. Well, remember, if you have, I'll write it here, if you have AB transpose, this becomes B transpose A transpose. And remember that A transpose transpose is A. So I can switch those two, A inverse A, and then say transpose. Okay, those two are equal. But what's in the brackets is the identity. And when you transpose the identity, you get back the identity. That means this times this is the identity. Therefore, the first matrix inverse is equal to the second matrix, or the second matrix inverse equals the first matrix. But we wanted to prove this, and we did. If you like videos like this, please subscribe to my channel. If you have any proofs that you like for me to make up a video for, leave that in the comment section. Leave any comment you like in the comment section, as long as it pertains to this video or my channel. As always, thanks for watching, and watch and learn.